So, welcome to lesson 11. In the preceding lesson, we learned that the Ireland-Claisen rearrangement proceeds via a six-membered aromatic transition state, which explains the stereoselectivity we have observed. Today's subject is stereoselectivity in Aldol addition reactions, and we will see that the stereoselectivity also in this case is explained by six-membered aromatic transition states. In this case, these are called Zimmerman-Traxler transition states. So again, also six-membered aromatic transition states. Well, aldol addition reactions, for instance, an aldehyde reacts with an enol. M is a metal. Here we have in focus an cis enolate or Z enolate. And this will result after hydrolysis. So first reaction at lower temperature, secondly, first reaction, hydrolysis. And this will give predominantly this beta hydroxycarbonyl group, and this reaction generates two stereogenic center. And if we start with the Z enolate, we will get predominantly the Zyn diastereoisomer, of course racemic. So predominantly Zyn, but racemic. It is clear that we have to pay attention with the hydrolysis process, because under more vigorous reaction conditions for the hydrolysis, we would observe then the aldol condensation process. So we should avoid eliminating water, which would then lead us to the alpha-beta unsaturated carbonyls, and our stereogenic centers are simply gone. So, avoid this. How could we explain the observed stereoselectivity? Well, as I said, six-member transition state. For getting to the six-member transition state, the Lewis acidic metal, it's a metal cation essentially, complexates at the carbonyl group, thus increasing the electrophilicity of that delta positive carbon. The reactive conformation should be drawn like this. So the metal coordinates at the carbonyl group. And now we can see we have those 6 centers which participate in the reaction. 1, 2, 3, 4, 5, 6. So let's put it like this. And then we will reach this situation. And in between, we have the transition state, where we would simply write those bonds in dotted lines. Well, as I said, this is the preferred conformation. Of course, in solution, we have also its mirror image, so that we get a racemic mixture at the end. Now we have to think about, well, what are other conformers that could, in principle, form an reactive intermediate. Sorry, not a reactive intermediate, but could go into that transition state. Well, simply change the R2' and that hydrogen. Let's see how that would look like. So, in the following transition state, we would have R2' in an axial position, just as this one. And those two groups, well, of course, would have a repulsive steric interaction. This is unfavorable. And this means that the equilibrium between this conformer and this one is predominantly on this side. And in addition, the activation barrier for the transition state should be lower in this case, which finally explain the stereoselective outcome of the process. So, let's have a look at special examples where we know what the substituents are, generally are. Well, okay, here a phenyl group with starting with benz aldehyde and lithium enolates with R one substituent R. So first, starting the reaction at minus 78 degrees. Again, careful hydrolysis. As pointed out already, predominantly the Zyn product should occur, as explained above. But with the trans, so with the anti-product as the byproduct. So if substituent R is very small, a hydrogen, well, we don't get any stereoselectivity. Well, we can imagine if R, so this here, is just a hydrogen, we don't have to bother with steric repulsion very much, and we don't get a good selectivity. No selectivity in this case. A bit larger, an ethyl group. Then we have a selectivity of 90 to 10. With an isopropyl group, it stays essentially the same, 90 to 10, and with a tertiary butyl group, we increase the selectivity to about 99 to 1. So this is then excellent selectivity. Another example where we reach 100%, almost 100% diastereoselectivity should follow now, and in this case it has a special reason, an additional chelate effect. Starting with this substrate with TMS protected alcohol here, LDA, THF, minus 78 degrees will give the cis enolate with the lithium chelated by the two oxygen atoms. So that enolate. Adding benzaldehyde at this low temperature, then the Lewis acidic lithium will coordinate in equilibrium to the carbonyl group of the benzaldehyde. So phenyl group here. Looks a bit crowdy with that large group in axial position, but it's only that hydrogen in the 1,3 diaxial position. And the lithium is very well coordinated. So a chelate effect goes through that Zimmerman-Traxler transition state. Now the lithium is bound to this oxygen. From the carbonyl it changed to become the alcoholate, and the lithium is still chelated by the other two oxygens. Well, to translate now this structure in stereo, to translate it in another drawing, and well, it makes sense to follow the rules of Kahn-Ingold-Prelog and determine the absolute configuration of the stereoorganic centers in this drawing. Then we will have an R here and S configuration at this position, and after hydrolysis we will get to the final product, this one. So, but of course, racemic. So we should put on those stars here. In literature, I found that one can oxidize a setup like that with sodium periodate. To get to the acid. So by oxidation you can get rid of this part. However, I would be careful with that information. I'm not sure that one does not have to protect that alcohol. Also, secondary alcohols could be oxidized under reaction conditions. Let's change to an interesting special case. It's known under the name Ivanov reaction. An instructive example, starting with phenylacetic acid and treating that with two equivalents of a simple alkyl Grignard. The first equivalent will of course react here to the most acidic position. We get the magnesium carboxylate, and the second equivalent is basic enough to deprotonate that alpha position. While the alpha position is still activated by the carbonyl group, but also activated because of a conjugation with a phenyl group. So we have the enolate of a carboxylate in this case. So, and it's clear there are no cis trans or syn anti isomers of this enolate. Do we nevertheless observe stereoselectivity, for instance, with a reaction with benzaldehyde? Indeed, we do. After hydrolysis, we will have anti and syn diastereoisomer, of course, racemic, and the selectivity is not that excellent, well, but 76 to 24, so approximately 3 to 1. How do we explain the selectivity in this case? Again, Zimmerman-Traxler transition states. We could have as transition state either this one and its mirror image, or well, okay, we could also change the phenyl group and that hydrogen. But as we worked out earlier, the phenyl group should remain in the equatorial position. It will become clearer with a Newman projection which will follow. Essentially, we should have a look at this configuration, or a second one where the phenyl group and that hydrogen change position. Based on the selectivity preferentially anti, observed in this case, we have to assume that this situation is favored compared to that one. Now the question is, why is this the case? Well, one tends to argue the phenyl group, this phenyl group here, in essentially an axial position of a chair-like transition state is disfavored. But why should it be disfavored? Axial position generally is disfavored because of 1,3 diaxial interaction. While there is no other axial substituent. So this can't be the argument here. In this case, it makes sense to draw a Newman projection of the transition state where we have a look to the axis of this carbon and that carbon. Okay, so Newman projection. Hydrogen, this carbon is that one. Here the other carbon with a CC double bond. That carbon is located behind this one. And, well, the magnesium is here. And if we want to draw the transition state, of course, we have to draw that as dotted lines. And there should be a dotted line between the carbon in front and the carbon behind. This would be the transition state. So, let's draw the transition state once again for this situation. Phenyl group here, hydrogen there. So what could be the explanation why this transition state is disfavored compared to this one? Well, now we can see that here in this area it is more crowded compared to this one. Well, and you should know the special expression for a situation like that. It is a so-called gauge interaction during the transition state. Here we have an unfavorable gauge interaction Well, in this case, with those two phenyl groups, we have also an unfavorable gauge interaction, but this situation simply is worse than that. That's the reason why this is preferred. Rather simple, okay? So the message is, in this case, the stereo differentiation has nothing to do with 1,3 diaxial interaction, gauge interaction we have to keep in mind. Next example, once again with benzaldehyde. It's obviously a test aldehyde for this type of reactions. But now a boron enolate with two N-butyl groups. This setup results in the Zyn product selectively of course racemic. Is that true? Yeah, well, let's count. 1, 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. Yeah, it's right. Of course, racemic. Zyn. And with better than 97% diastereoselectivity. So this is quite remarkable compared to what we are used to with lithium enolates. Generally, the diastereoselectivity of the aldol addition processes with boron enolates is much better than with lithium enolates. The reason for that simply is that the oxygen-boron bond is much shorter. Well, it's about 1.5 angstrom, whereas with lithium enolates we are in the range of 2.0 angstroms. So, if you then compare the transition state the system has to run through, the transition state with boron enolates is more compact. And therefore, those steric interactions and gauge interactions and so on, simply work better with a more compact system. Moreover, with boron enolates, it is very well tested how to get to the Zyn and anti-enolates. For instance, starting with this is simply pentanone. Typical reaction conditions. For VZ enolate. Are the corresponding triflate applied, then diisopropyl ethylamine also known as Hünig's base, reaction in ether at minus 78 degrees, 30 minutes, and we get the Z-enolate with high selectivity, 97%. Next step, reaction with benzaldehyde at the same temperature was tested to give (99% Zyn, of course, always racemic. Let's change reagents a bit. 2 cyclohexyl groups at the boron, and not a triflate, but a chloride. A less sterically hindered amine, triethylamine. Same solvent, diethyl ether, same temperature, a bit shorter reaction time, 10 minutes, and astonishingly, we get predominantly the E-enolate with better than 99% selectivity. Reaction with benzaldehyde consequently leads to the racemic anti-product with better 97%. So, how can we explain the difference? Without going into details, most important difference between those two reaction conditions is that we have the triflate here and the chloride there. Because of the triflate, this boron is much more Lewis acidic. In this case, the boron will attack that carbonyl before that ketone is deprotonated. So, in this case, we have this situation as a reactive intermediate this is deprotonated. And this indeed makes a difference. You see it in the outcome. Here, this is far less Lewis acidic. Therefore, the triethylamine generally has to deprotonate first with carbonyl, and then the boron attacks. I think this is essentially the difference of those two systems. Well, what we can also learn from literature is if we somehow have the wrong enolate, we can find reaction conditions for the cis-trans isomerization of the enolates. Well, in that case, we will get the thermodynamic equilibrium. This can be done with buffered systems. For instance, pyridine in combination with an acid. Or also, it's in literature treating it with simply pyridine at higher temperatures. So, there are some possibilities for the equilibrium. Lutidine triflic acid at 70 degrees was introduced, I think, by the Evans group. I hope you remember a special case of aldol addition reaction we already talked about, Mukayama aldol addition. For Mukayama aldol addition, we have silyl enol ethers as substrates. For instance, this TMS enolate. We talked about Mukayama aldol in connection with Ireland-Claisen rearrangements, I think. So, and the aldehyde. Generally, with Mukayama aldol, the electrophilicity of the aldehyde has to be triggered, to be increased by a Lewis acid. Could be titanium tetrachloride, for instance. So, we have a Lewis acid coordinated at the carbonyl group. So, also in this case, we will get some stereoselectivity. But I think it's important to know that in Mukayama aldol, we don't have a Zimmerman-Traxler transition state. We don't have a closed aromatic transition state because the silicon is not a Lewis acid good enough to coordinate at the carbonyl group. And as we have seen, we need a stronger Lewis acid to get the activation done. Okay. Nevertheless, we can achieve high diastereoselectivity and even some enantioselectivity if we apply chiral Lewis acids. Then we have chiral information already in the system. So, just these remarks for the Mukayama aldol addition. Then a special case is aldol addition by organocatalysis. This has, per definition, nothing to do with stoichiometric organometallics, but we have we have to have a closer look to competing systems, competing with organometallics. So, what can we achieve with organocatalysis? Catalysis with small organic molecules. Let's take propionic aldehyde and the most typical organocatalyst, proline. We need 10 mole% of this amino acid. Reaction performed in dimethyl formamide at +4 degrees will lead to the formation of this homo-aldol addition product. We get an 80% yield, 4:1 anti to Zin, and moreover, since we have chiral information in that system, a 99% enantiomeric excess. How does this work? That secondary amine forms an enamine by condensation with the aldehyde. With a hydrogen bridging bond, the second equivalent of the aldehyde is coordinated to the system, and this is activated. In this sense. Well, and the chiral information is transferred. So, that anti-Zin selectivity is well, certainly not as high as with the boron enolates, but the 99% enantiomeric excess, this is convincing. So one could ask, of course, why do we need this organometallic aldol addition, where we now have organocatalysis as a powerful instrument? So there are some methods that still have much importance and will it also have in future. The best known is Evans enolate chemistry. Which is a method for first diastereoselective setups and enantioselective at the same time with stoichiometric organometallic chemistry. So let's see. Add the carbonyl moiety, which has to be transferred in the aldol addition process. We have this chiral oxazolidine, as a chiral auxiliary. That means that part of a structure transfers chiral information. And afterwards, we have just to break that nitrogen carbonyl group, and hopefully we can recover the chiral auxiliary. So, working with boron enolates, synthesizing the Z enolate, and let it react with simple aldehyde. Oh. Will give this product Diastereoselectivity 99.6%. This is a general trend. For instance, with benz aldehyde, well, this translates to about 250 to 1 with the benz aldehyde. We will have a phenyl group here at this position. Then we have even 500 to 1 and a 95% yield. So, an excellent reaction. And moreover, what is very important is these products are normally crystalline and they easily crystallize. So one recrystallization normally purifies it even further, that you have in the product 100% diastereoselectivity. And it's then enantiomerically pure because the chiral auxiliary that you put in should be enantiomerically pure. Hydrolyzing this nitrogen carbon bond should then lead to the pure enantiomer of that acid. Actually, this is not so easy. How do you hydrolyze this bond with not eliminating water here? But you could do other things. You could put in a protective group here. You could reduce that carbonyl group to an alcohol. So, hydrolyzation would then, because it's an aminol, would lead to the aldehyde. You could then use this aldehyde again for a second aldol addition process with Evans enolate. Then you have already 4 stereogenic centers in one row. This is an excellent method for building up rather complicated target molecules. Very reliable. So, and where do you get this chiral auxiliary from? Well, of course, from chiral pool, you should certainly know. In this case, it is Valen reduction with lithium aluminum hydride gives the chiral amino alcohol, and treating that with diethyl carbonate under suitable reaction conditions will give you the oxazolidine. Last example for today. A combination of Evans enolate aldol addition and Ireland Claisen rearrangement. Let's see. So, the Evans-Barone enolate treated with acrylic aldehyde. Fortunately, instead of Michael addition process, we get 1,2 addition. Having an allylic alcohol at the end of this chain. More than 99% diastereoselectivity, reduction with lithium aluminum hydride, will lead to this alcohol enantioselectively pure. Base and an silyl chloride will introduce the protecting group preferentially to the primary alcohol, since this one is sterically less hindered. Then we can acylate the secondary alcohol with LDA minus 78 degrees, trimethylsilyl chloride present, we will get the ester enolate. So, and the Claisen rearrangement after hydrolysis will lead us to this final product, where we obviously have a 1,5 relationship between two stereogenic centers. Obviously a nice example for a remote chiral induction. And we have lots of functional groups with which we could do various things, reducing that to an alcohol or oxidizing that to an aldehyde, making use of that olefin. Certainly an interesting system. Well, enough for today. Thank you for listening. See you next week.